Hi class, today's video is about the endurance limit of real parts. So what I want you to get out of this little video series, starting with this video, is you'll be able to calculate the endurance limit S subscript E of a real part given the endurance limit of a test specimen, which we'll also learn to approximate just based on the ultimate tensile strength of the test specimen, or of the material really. Also information about the surface condition of the part. Is it smooth? Is it rough? The size of the part. Turns out that bigger and smaller parts have different response to fatigue conditions. The load type of a part. Is it going to be under axial load? Is it going to be under torsion load? Is it going to be under a moment load? What the operating temperature is. Turns out if it's a little bit warmer than room temperature, you're a little bit better off in fatigue. But if it's too cold or if it's too hot, your fatigue strength is going to go down. The reliability of your part. So a lot of tests are done and they determine what the strength is, and they say, all right, there's a 50% chance that it will fail at this life or greater. There's a 50% chance it will fail at this life or less than that. And that's the number that they give you. So if you need to be more reliable than 50%, then you're going to need to adjust that strength number when you design your part so that you make sure that 90% of the time that your part is going to exceed the life that you designed it for. And any other effects, it turns out there's a lot of other factors that could affect the fatigue response of a part. So this video here is going to introduce the difference between the endurance limit of a specimen tested in the lab and a real part by modifying the endurance limit that you get from a lab specimen by all these different factors. So let's start off by recapping the SN diagram. So S stands for the strength or stress, and N is for the number of cycles to failure. So on the horizontal axis, we have the number of cycles to failure. It's on a logarithmic scale, so orders of magnitude appear to be spaced evenly. And on the vertical axis, we have the fatigue strength of an ideal specimen. And by ideal, I mean it has a mirror polish, we're testing it at room temperature, we're applying also this perfect load in bending. Turns out when you apply this arrangement of forces, then the center region of the part is going to get a constant bending moment throughout it. Everywhere between these two applied forces is going to see a constant bending moment. So think about how when this specimen rotates, then if I'm a material point, I start off here at the very top of the part, and I've got this compressive bending stress, and then I rotate around towards the front of the part, and now actually because of the way it's bending, I'm not seeing any stress at all. And then when I rotate to the bottom of the part, then I'm under a tensile stress, a purely tensile stress. And what the profile of that load looks like is a sine wave. From my perspective as a point on the part, I am subject to compressive and tensile stresses, and the magnitude of the stress varies according to a sine wave. Okay, so now we need to fill in the graph. We're going to rotate this beam specimen, we're going to apply a different load to it, and we're going to plot points on the graph. So let's say we apply a bending moment such that the amplitude of the stress that is seen by points on the outside of the part is the ultimate tensile strength of the material. How many cycles is this specimen going to last for? Is it going to last for a really long time, considering that we're applying the ultimate tensile strength of the material? Think about that for just a second. How many cycles can the specimen endure at this stress SUT, the ultimate tensile strength of the part? It's going to be right here on the far left, right? It's the ultimate tensile strength. It's the maximum stress that material can handle. It can handle one cycle of application before it fails completely. Now I'm going to do the test at a different level of load, and I'm going to record the number of stress cycles at which the specimen fails again. Now it's a lower load, so we'd expect it can handle more cycles. It turns out for this material, the point might appear here. And so we can do that for a lot of different stress levels and plot the points at which the part fails, and it turns out that they all form sort of a straight line between them. For at least for a low number of cycles, or relatively high stresses near the ultimate tensile strength, on a log-log plot, the points of failure form a straight line. Now once we get past around 1,000 cycles, it looks like it's between 100 and 1,000 on this plot, the slope of the line changes. You plot a bunch more points at lower stress levels, and it appears that the slope of the line has changed, but it's still a straight line. And we're going to get towards, we'll talk about approximating what these straight lines are a little bit later. But for now, it's just a good idea to get the gist of things, that these plots form straight lines. Until we get around 1 million cycles. Once we get to 1 million cycles, we can apply around, 50 KSI here, and it turns out we're going to get a lot of scatter in the data. We're applying just about 50 KSI as the stress to the part, and we're seeing points appear at wildly different lives, right? Some last for 10 to the 8th cycles, some last for just 1 million cycles. The curve has straightened out completely. But this is important, okay? This means that if we apply a lower load than that, we get infinite life. If we apply a lower stress, then it doesn't matter how long we run it for. We'll get up to 10 to the 9th, 10 to the 12th. It will continue on forever, at least for steel. Many types of steel have what we call an endurance limit, where the part never fails. And we give that endurance limit, at least for the ideal test specimen, we say S subscript E. S is for strength, E is for the endurance limit, and the prime indicates that we're talking about an ideal test specimen here. We observe that if you apply a stress level below this endurance limit, then the test specimen will last forever. And so you think, okay, so this is how I can design a part. Normally, when you've designed a part, you've tried to avoid yielding, right? And so you've said, I'm going to apply this static load. I'm going to make sure that I design my part so that the stress level stays below yield. Okay, but now we say we need to last for 10 to the 4th cycles. Instead of designing to make sure that you stay below the yield strength of the part, we're going to say, all right, it needs to last 10 to the 4th cycles. I'll draw a vertical line there. And it's going to tell me, all right, I need to stay less than around 73 KSI in order to avoid my part failing. And you'd be right. That's the right sort of idea. At least for the test specimen, if you apply a stress of 73 KSI, then you're going to get about 10 to the 4th cycles out of it. Sometimes a little bit more, sometimes a little bit less because of the data, but you have the right idea. You could design, if you had ideal conditions, if you had a mirror polish finished on your real part and you're going to apply loads on it just like you apply loads on a test specimen, then you'd be right. You just need to stay under this 73 KSI, and you'll have about a 50-50 chance of getting 10 to the 4th cycles out of it. But as we said, this is only 50% true. Sometimes you're going to get a little bit more. Sometimes you're going to get a little bit less life out of it, about half the time. And it's only true if your actual part is perfectly polished, like the ideal test specimen. If it is a rotary beam, right? So you're applying this bending moment load and it's sinusoidally varying. If it is subjected to, a bending load and not an axial load or torsional load, and it has to be done at room temperature. If you're a lot colder than that in your operating conditions, you're going to have a lot lower fatigue strength. Real parts are not so lucky. They do not enjoy the same conditions of the tensile test specimen. And so it turns out that the curve looks something more like this. Everything gets reduced, especially up in the high cycle fatigue range. Your endurance limit drops, and these points drop accordingly. And so if you're designing a part, and if you happen to know what this curve is, precisely, if you have data for your actual part, then you can say, all right, I need it to last 10 to the 5th cycles, then I need to keep the stress in my part under, say, 50 KSI. But the problem is we don't have this data for our real part before we design the part, so we're going to have to estimate it. And it turns out there's a nice relationship between the endurance limit, SE prime, of a test specimen and the SE, the endurance limit of a real part, based on things that we can measure about our part and things that we know about the operating conditions of our part. We'll learn to approximate what this SE is. So it turns out that the formula that you can use to estimate what we call the fully corrected endurance limit, where we've dropped that prime symbol, SE, we've dropped that prime because we're no longer talking about the ideal test specimen, we're talking about our real part, is equal to our SE prime, the endurance limit for a specimen made out of the same material as our part, But we have to account for all these different factors. We're going to multiply it by a bunch of different factors, most of which are less than 1, accounting for different conditions. And these are called Marin factors based on the engineer, the name of the engineer who first studied them. So in the next few videos, we're going to learn how to estimate what the values for all these different factors are based on the conditions and things that we can measure about the part so that we can estimate the endurance limit of our part from the endurance limit of a test specimen of the material our part is made out of and all these other things that we can measure.